Hey guys, STAT1800. The purpose of this video is ultimately to uh, introduce you to the F distribution. And the F distribution is kind of unique. We've looked so far at the T distribution and the Z distribution. The F distribution models our ANOVA decisions. And it reminds you a lot of the chi-square distribution, which we'll use later on in the term. So, guys, I think it's kind of good before, again, I'm a firm believer, before we learn something new, let's embed it in something that we've done previously. Remember the Z distribution follows a normal distribution with a mean 0, standard deviation 1. There's only one of those, right? But we saw that the T distribution follows a T distribution with a particular degree of freedom. Now, the degree of freedom in this case is easy to find, easy to calculate. It's just the total sample size minus 1. Now, something interesting, as your degrees of freedom increases, the T distribution actually approaches the Z distribution. And you can see this by examining the Z critical for a 95% confidence interval. Now, if we're living, with the Z distribution, we should know now that value, the Z critical for the 95% confidence interval, is plus or minus 1.96. But when we have the T distribution degrees of freedom, say for example 10, we should know that we can go to StatCrunch, go to our calculator, go to T, and really the easiest way to do that is do between and do 0.95. And we can see that our T critical is plus or minus 2.228. Now, here's what I'm going to do. I want to illustrate how this number becomes closer and closer to 1.96 as our sample size gets larger. So if our degrees of freedom, which is clearly a function of the sample size, increases, then our T distribution essentially becomes the Z distribution. So if I let the degrees of freedom increase, so let's go to 20, and let's go degrees of freedom equal 50, and then let's go T degrees of freedom equal 100, and then let's go T degrees of freedom equal 300, and make a note of well, this would be Z or T critical, right? This would be a Z critical. This would be T critical if we're dealing with the T distribution. So, guys, I could go degrees of freedom 20 with 0.95, and you can see that my T critical is 2.085. And then let's go degrees of freedom 50. So we're plus or minus 2.009. Now let's go up to 100. So now we're plus or minus 1.984. And let's jump it up a whole lot to 300. And we can see it's plus or minus 1.968. So back to the chart of values. Where's this thing headed? Well, as our degrees of freedom get larger and larger and larger, you can see that our T critical becomes smaller and smaller and smaller, and it seems to be approaching this 1.96, which it is. So guys, again, as your degrees of freedom increases, magically right in front of your eyes, the T distribution becomes the z distribution. Okay, the purpose of this video, though, is to look at this F distribution. And guys, remember, the F distribution has 2 degrees of freedom. We'll call it degrees of freedom 1 and degrees of freedom 2. Now, for the sake of the ANOVA problem, the degrees of freedom 1 is the number of groups minus 1. The degrees of freedom 2 is equal to the total sample size minus the number of groups. So for the golf club problem, we had 15 total clubs, or total drives. There were 5 with each club. 5 clubs, okay? So our degrees of freedom would be the number of groups, which is 3 minus 1, gives us a degree of freedom 2. And our degree of freedom, our degree of freedom 1 is equal to 2. Our degree of freedom 2 is the total sample size, which were 15. Remember, we had 5 clubs with 1, 5 clubs with 2, 5 clubs with 3, right? So we had 15 total sample size minus 3 clubs. So our degree of freedom 2 would be 212. Now, let's just examine that. And first of all, let's find the critical value for alpha equal 0.05 for this problem. Now, guys, the F distribution is not symmetric. The F distribution is a positively skewed distribution, and all of our rejection region goes in the right tail. So we need to find the F value that separates the bottom 95% with the top 5%. Now, why 5%? Well, we're looking at an alpha 0.05. So we have 5% of our area under our curve designated as the rejection region, which aligns with our alpha value. So we need to find the value, the F statistic, in this distribution, degree of freedom 2, 12, that has 5% of the area to the right. Well, guys, StatCrunch makes it very, very easy to do that. Maybe. Okay. All right, so let's get rid of this. We're no longer looking at the T calculator. We need to go to Stat Calculator, and as you would probably expect, it's called the F calculator. Now, the F calculator is a little larger. All right, so we need the standard, and I need degrees of freedom 1, so I need that to be 2. And I need my second degrees of freedom to be 12. They call it the numerator and denominator degree of freedom. That'll make more sense when I actually do some of these calculations, okay? And I either want this to be, if I do less than, then I need to put a 0.95 there. If I do greater than, I need to put a 0.05. So I'm just accustomed to looking at the area above. And we can see from our table that the critical value of 3.885 separates the top 5% with the bottom 95%. So our critical value here would be F star equals 3.885. So guys, back to the drawing. Our F critical would be 3.885. Now, remember in the ANOVA calculation that the F statistic is the ratio of 2 things. The mean square among divided by the mean square within, where the mean square among is the sum of square among divided by the degrees of freedom among, and the mean square within is the sum of squares within divided by the degrees of freedom within. Degrees of freedom, if you think about this whole thing being in the numerator, this whole thing being in the denominator, degrees of freedom for the numerator, degrees of freedom for the denominator. So that's where STAT crunch is getting that whole NUM and DEN denominator business. Okay? So then we come out with this F statistic value. Now, what we'll typically do, though, is we won't use the critical value approach. We will use the p-value approach. So let's say that our F statistic turns out to be 4.12 after all the smoke clears from this calculation right here. Our F statistic, not our F critical, our F statistic turns out to be 4.12. We're drawing from a F distribution with degrees of freedom 3, 27. Do we have significance at the 0.05 level? Well, what we'll do is we'll calculate the p-value. So we have an F distribution, degrees of freedom 327, which is going to look something like this. Our F statistic is equal to, what did I say, 4.12? So essentially, guys, what are we looking at? We're looking at the area right of this, and if that area is less than 0.05, then we have statistical significance. If it's greater than 0.05, we don't. So how are we going to do that? Well, guys, we're going to do it the same way. We have degrees of freedom 3, 27, and we want the value to the right of 4.12. So our area to the right is our p-value. Writing this down so it'll be available when we get over there. 0.016. All right, let me show you what I've written. So our p-value is 0.016 because it's the area to the right. Guys, again, F distribution, none of that two-tail stuff. Don't have to multiply by 2. We only worry about the calculation in the right tail. So the area to the right of 4.12 is 0.016. That's less than the level of significance 0.05. So if this was an ANOVA problem that we're working, we would reject H sub O. Conclude at least one pair of means is different. And to examine that more closely, we would conduct a post hoc test. And there are a lot of these out there. But we will conduct a Tukey HSD. The reason we conduct a Tukey HSD is it's the only one that's available on STAT crunch. Plus Tukey. I mean, Tukey's probably the greatest, one of the greatest statisticians ever. So it is a very commonly used post hoc test for an ANOVA. So, guys, that's all I got here. We'll get into an example that I will work through. I'll calculate the sum squares and both sources, and we'll do the whole very in-depth example in the next video for ANOVA. So guys, take care.